Hello folks, so in this video I want to talk about how we can use the vertex form to find the x-intercepts. Okay, so we have two examples here. The first one we'll just start off with on the left here, 3 times x minus 2 squared minus 27. The second one actually looks very, very similar. It's 3 times x minus 2 squared and then minus 5. We see some interesting things with between these two examples, but let's start with the one on the left. Okay. Now, whenever you're finding the x-intercept, your first step, again, no matter what type of equation you see or what type of function you got, your first step is always set y equal to 0. Okay, so I'm going to start off with 0 is equal to 3 times x minus 2 squared minus 27. Okie doke. Now, you have a couple ways to go about this. One way to do this is that you could multiply this out and, expand everything and then get it into standard form, and then try to factor it, and then use the zero product property. That will sometimes work, but as we've seen before, that doesn't always work because not every quadratic function is factorable. And so I don't want to have to go through that and then be disappointed at the end when it's not factorable. So we actually don't need to do that because we can just solve the equation, well, as is. So the way I'll do that is I'll add 27. So I'll add 27 to both sides. We'll get 27 is equal to 3 times x minus 2 squared. We've seen things like this before. And again, if you're unsure, right now, you can, from the very beginning, you could always kind of just substitute this and just call this, I'll call it y. Or maybe y is not a good one. Maybe I'll call it w. So maybe I'll just rewrite this as, 3 times w squared. And that's fine because, again, at the end of the day, we're just going to substitute, so we're just solving for w at the moment. Okay, so I'll divide by 3. Again, so what we did right here at this x minus 2 substitution is we just kind of put a disguise on it. And that's totally fine to do, as long as we remove the disguise at the very end. So I'll divide by 3, and I'll get 9 is equal to w squared. Okay. And now, we undo squaring by taking the square root of both sides. So this is really nice right here because, again, the idea here is that the square root function and the x squared function are opposites, so they undo each other. Again, similar to how addition and subtraction undo each other. And then we'll get, w equals 3. W equals 3. Now remember that w is not what we're looking for. We're looking for x, but w equals, not 9, 3. And so if I remove the disguise now, we will end up with 3 is actually equal to x minus 2. And then we'll add 2 to both sides to get 5. So x is equal to 5. Now, this is kind of awkward because you remember that most quadratic functions actually have 2 x-intercepts. And we actually know that this one should, because, for example, we know that the vertex of this function, the vertex is at 2, negative 27. Again, see the previous video for why that is the case. But this is where the vertex is. So the vertex exists down here. And because a is positive, we know it opens upward. So it's going to open something like that. So I found one x-intercept, but where's the other one? Well, we come back to this. Let me just clean this up here. It comes back to this step where, if w squared equals 9, there's actually 2 options for what w could be. It might equal 9, in which case, it might equal 3, because 3 squared gets you to 9. But at the same time, it might be negative 3. Negative 3 right here. Okay? Because again, and we just check. Well, negative 3 when you square it, negative 3 times negative 3 is going to get you to 9. So negative 3 is a solution here. Again, it's a solution for w. So when I solve this, well, again, it will say x minus 2 is equal to negative 3. And if I add 2 to that, then we'll get, one solution again is x equals 5. The other solution is x equals, negative 1. And so that is our second x-intercept. Okay? basically what we got from here, and this is the key takeaway right here, is that if w equals the square root, w squared is equal to 9, then w itself could be positive square root of 9 or the negative square root of 9, i.e. 3 or negative 3. We're going to want to hang on to that. Okay? Let's try the same procedure over here. So again, we'll start off, set y equal to 0. Equal 5. And again, our process is going to look near identical. So we're going to add 5 to both sides. And we're going to get 5 is equal to 3, x minus 2 squared. We'll divide both sides by 3. We'll get 5/3, x minus 2 squared here. Okay. So now we get the same thing, is we're going to want to take the square root of both sides. And again, just like before, on the right side, the x squared, the squared and the square root function undo each other. But this thing on the right, it doesn't quite have this nice square root like the other one did before, because 9 is a perfect square. 5/3 quite clearly is not a perfect square. But that's totally fine. Right? The square root of 5/3 is some number. And I don't know what it is, but it is some number. Okay, so we're just going to leave it like that. It's totally fine. And so just like before, again, there should be two answers, right? It might be the positive square root of 5/3. So we'll get x minus 2 is equal to 5/3. And technically speaking, let me kind of fix this here. Just kind of not really fair. Because it can't be either that. Or w equals negative 3. Equals negative 3. All right, sorry about that. So over here, one answer is the square root of 5/3, or it might be the negative square root of 5/3. And again, if you're not sure, double check by squaring it, right? So if I take the square root of 5/3 and I square it, well, of course it will get 5/3, and that's totally fine, right? Because x squared and something squared and the square root, they undo each other. If I check over here, again, this is not the square root of negative 5/3. It's the square root of 5/3 with a negative sign in front of it. And when I square that, well, again, negative times negative is a positive. So it does end up being, again, positive 5/3. And so, again, this is how you always end up getting those two solutions. Because, again, there is a possibility of having two solutions. You might have only one solution, and that happens in a very rare case. But a lot of times you will have two. And this is how you get the second one. And now to get this, to get x by itself, we'll add 2 to both sides. And you're going to end up doing this on both of the equations. And you're going to get, on the left side here, you're going to get x is equal to 2 plus the square root of 5/3, or 2 minus the square root of 5/3. Okay, and these are your two x-intercepts. Now again, this is what we would call the exact form. Okay, why? Well, because that's exactly what it is. The two x-intercepts are 2 plus the square root of 5/3. That's one of them. And the second one is 2 minus the square root of 5/3. The reason we call it exact as opposed to approximate, and I'll drop that right here, is because there is no doubt what they are. But in order to actually graph them and actually put them on your graph paper to sketch the parabola, you're going to want to actually use the approximate form so that you actually know where to put the points. So the approximate forms are basically using your calculator. So let's see, if I use my calculator to double check what these are, let's see, 2 plus the square root of 5/3, I end up with about 291. And these are approximations. And the second one, if I change that to a subtraction, I'll get 0.090. Sorry, 0.709. Okay. Again, these exact forms are important because they will come up. Because They're important because this is the most accurate way to give the answer. Okay. For example, if I actually plug this point in for x into the original function, you won't get 0. You'll get something that's very, very close to 0, but not exactly. The only way to make sure 100% that you actually do get 0 is to literally plug this value in. Okay. Again, these are irrational. And I won't go too far into what makes an irrational number, but an irrational number
hello, Mr.
is
Chang.
a number that is an infinite non-repeating decimal, and this is what that is. Okie dokie. So we're back. I'm back from that little impromptu visit. But yeah, an irrational number is an infinite non-repeating decimal. What does that mean? Well, think pi. So pi, you've heard this before. It's got 3.14159, etc. That's as far as I can remember. But there is no pattern to those repeating digits. Contrast that with 1/3, which is 0.3 repeating. This is an infinite decimal, but it does repeat. And so this is still a rational number. A rational number. Okay? And so this is why certain quadratic functions cannot be factored. For this one, and you should try this on your own, you should try to multiply it out, get it into its standard form, and try to factor it. You'll find you won't actually be able to do it, again, not using whole numbers. Okay? So not every single function has a vertex form because every quadratic function has a vertex. However, not every function has a nice factored form because not every quadratic function has nice rational x-intercepts. Okay? For example, because this one has x-intercepts of 5 and -1, we know that the factored form will end up being something like this. A x minus 5 times x plus 1. And you would have to figure out what a is. Over here, it wouldn't quite work out the same. I mean, technically speaking, you could write it like so, equals some a and then x minus this number, x minus 2 minus 5/3. But again, you would never have guessed that from the very beginning in the first place. And so the only reason that I could write it like this is because I know what the answer is. So anyway, that's how you could use the vertex form to find the x-intercepts, and I hope that helped. Alrighty, so thanks for watching, and I'll catch you later.